Hi, I'm going to talk about how to use the t-distribution to find the population or the confidence interval for the population average given a sample for which you found the average for. Even if it's a smaller sample, the t-distribution tends to be better for making these kinds of calculations as long as it's normally distributed in the population. Also, I will talk about how to find the confidence interval for the difference of two population averages given two sample means. So to start out, and two sample variances. So to start out here, I'm going to tell you about my key. So whenever you see sigma squared, that refers to the population variance. Just sigma by itself is the square root of the variance, so that would be the standard deviation of the population. S squared is the variance of the sample, and the variance of the sample is calculated a little bit differently when you want to look at when you want to learn about a larger population, particularly if you're actually pulling without replacement even. If we were to go back to a couple of videos ago, when you look at the variance, it works out that it's actually better to use n minus 1 in the denominator when you're calculating the variance. Even though you're adding up the variance of all n, it has to do with what's called degrees of freedom. And in the t-distribution, to find the value of t here in this table, we're using degrees of freedom. And degrees of freedom are if you're just looking at like one sample, you're not pooling two samples together. You're going to just look at the actual number in the sample minus 1 for your degrees of freedom. And that's how you find the row, and then you look for the confidence interval that you want, or the confidence that you want. So if you do 95% confidence, these are the values that are corresponding to degrees of freedom of 1, 4, 9, and 29, which are this. For n, that's 2, 5, 10, or 30, if you're just looking at one sample. So it's a little bit different, but the concept's the same, and it just has to do with replacement, without replacement, and degrees of freedom. That's why we use n minus 1. But when we're looking at the average, like when we're looking at the actual average of an average, or the expected value of an average, and we were calculating the variance of that. In that case, we just used n, and it's okay to use n in that case. But when we're looking at a sample size, and we want to look at that compared to, like when we're looking at a sample, and then we're looking at the larger population, when we work with variance, it's better to use n minus 1, at least, in degrees of freedom. So whenever you see s squared, that's the variance of the sample. Just S is the standard deviation of the sample, which has, I guess, limited utility, but for these formulas it's fine, because we're using n minus 1. Z, we talked about Z in the previous videos. That's the, actually we should put a line over X actually. Well, it depends on how you're thinking about it. It doesn't have to be this way. It could be xi. But you're looking at each individual value, you're subtracting the average, and then you're dividing by the standard deviation of the larger population there. In this case, yeah. So you're dividing by the standard deviation. That gives you a z value, which is basically the number of standard deviations away from the average that this value is here. And that's the standard deviation. So if you want to think about it as dividing something by 1, you get that number. Well, the same kind of concept applies here. You're looking at that value and you're comparing it to the actual value for one standard deviation. I think it was like 68% or something like that is within one standard deviation on either side in the normal distribution. But then for 95% confidence, it's 1.96. And then 3 is like, I don't know, I want to say like 99% or something like that. Don't quote me on that, but I think it might be right. But for T T uses a different strategy. So this is the Z. The Z, we have a normal distribution, just one function here. For T is basically it's basically the average of a sample minus the population average divided by the sample variance divided by n, the square root of n. So notice that this is the sample variance, and notice that in the previous ones that we've done, we've been using the actual variance of the population. It's okay to estimate sometimes with Z and just use the sample variance like I did in the last video. But for the T distribution, which is going to be a little bit more accurate for, it gives a little bit of wider confidence interval basically for values when you have fewer in your sample, which is good to do. So it kind of compensates for that because there's a little bit of uncertainty. We're using the variance of the actual, or the standard deviation of the actual sample here. And we don't know what the actual standard deviation of the original population is, but using the degrees of freedom and the function for T, given degrees of freedom, which is usually one less than the number if you're looking at the sample, it works out better. df is degrees of freedom, and I use that here in this column. If you see s squared, once again, that's calculated. You're taking each value, you're subtracting the average, and then, oops, I forgot about the squared. You're squaring it up here. And then you're dividing by n minus 1. And when you see alpha, which actually I don't even use, don't worry about that. Confidence interval, Ci, whenever you see that. And I use subscripts for different kinds of methods for the confidence interval. So for the T distribution, so in this case, n is less than the green n and less than the red n, right? So if it's a lower n, you could still have values out here more than you could have it for, say, if the n is much larger, it's not going to be out here as much. And we talked about this. Basically, when you look at even the average, so if you look at the average of a sample, if the n is really large, remember, the variance of the average is going to be about 1/nth of an nth in terms of the sample size. It's going to be about 1/nth of the larger population variance. Because you're taking a bunch of values, they're canceling out variance-wise, so you get a narrower area for where the actual average would be. Even though you have one value, you don't know what it would be for sure, it's still not going to deviate that much as n gets larger. So that's the concept behind this. So if we have a small n, we still don't really know for sure where it is, so we leave more area here under the curve on the sides, but we don't go up as high in the middle. But for a little bit larger, we don't need as much area out here because it's not as likely out here, but it's more likely in this narrower area. And then for an even larger n, it's going to be more confined to the center. So these areas have to be all equal for all of these in this function if you were to take it infinity in both directions. So it's going to end up narrowing, and most of the area is going to end up in the middle. So that's what the T distribution does. The T distribution takes into account what are called degrees of freedom, and that's basically dependent upon the number in your sample size. So that's what the T distribution is. It's a little bit better than the Z distribution. As long as it's a normally distributed sample, normally distributed population, it's going to be a little bit more accurate to find a confidence interval for you. Because we don't actually know what the variance is in the population. Whereas we can use Z, but n needs to be pretty large, needs to be larger. But if you have a smaller sample size, you can still look at degrees of freedom for even 1, 4, 9. But notice how large it is for 1. That's like 6 standard deviations, right? That's huge. And then if you keep going up, it actually rapidly changes when you get to 3. It's kind of like the change is a lot here, but then it becomes a lot less as you get higher, which we would expect. So the confidence, so it's good for small sample sizes. It assumes a normal distribution. If it's not a normal distribution, you may not want to use T. In fact, you may not even want to use Z sometimes, but if it's large enough, you can use Z. So the confidence interval equals the sample average plus or minus the reliability coefficient. I never used this term before, but that actually refers to Z or T. That's what that means. So the Z or the T is the reliability coefficient that we're multiplying times the standard error to get within that confidence to get what you need to add or subtract from the value you got to determine what the actual real value in the population might be. Okay? Confidence interval of the actual average of the population. Remember mu, actually put that there. Mu is the population average. And when we're using the Z reliability coefficient, we would take X with a line over it, that's the average of our sample, plus or minus the reliability coefficient of Z that we found before. And how do we find that? We basically took the variance of the, excuse me, we divided by the standard deviation, and we found the actual difference, the uncertainty or the difference, the variance, and then we divided it by the standard deviation. Or no, sorry, I got that wrong. No, it was over this, I'm sorry, give me a second. To find Z, you divide it by the standard deviation, but this is basically the standard deviation is on top. The standard deviation of the actual larger population, or your estimate of it, which you can use by, if you're considering n. So you get Z, and then you multiply that times the square root of the variance divided by n. If you take the square root of the variance, you get standard deviation divided by the square root of n. We talked about that before. But for t, we're using the sample. So instead of using the population variance, which we can kind of estimate if it's a large enough sample, if it's a smaller sample, we got to really consider what is our actual sample, because that's small and the variance may not be exactly right. It uses degrees of freedom, n-1, and you can at least get a larger swath, but it's not as large for larger numbers, which is why the t-distribution is better for those kinds of situations when n isn't as large. You take the square root of that variance for the sample size divided by the sample variance divided by the sample size. So this would come out to be the standard deviation of the sample divided by the square root of n. But you're taking it times t. And t you find using the number of the sample. So if our sample number is 30, we want to come down here. We got to subtract 1 from 30 if we're just looking at an individual sample. That's 29. And then we find that it's 1.6991. So we want to take 1.6991 times the standard deviation that we found here, the standard error of what we got for our average, what we'd estimate the actual standard deviation would be, the spread of to getting that average, which depends upon the actual variance of the original population, which we don't know, but we're estimating, and also the number that we have in our sample, because as we get larger, we're canceling more of those variances to get that actual average, to get the total at least, and then we're dividing by whatever n is. So we're basically canceling out some of those variances. It's less variable, and that's why we do that. So confidence interval of t for the difference of two means, though, we want to actually take into account the fact there are two different situations. Say we just want to see, are these two sample sizes really representative of each other, but they're kind of small, they don't have a large sample size, and we don't know the variance of the other populations. We want to just see, let's assume that they're the same variance from the same population, and let's see what the probability is of having two values like that, that are that different from one another for averages and the samples. When we do that, we're just going to assume the variances are the same for whatever that population is, and we're going to actually use the variance, a variance value that's representative of the two samples. Because we already have two samples, using just one of those, we might as well try to use the other one too, the other variance for both samples. So we have to get the pooled variance, and to get the pooled variance, which is represented by s sub p squared, we want to take n minus 1 because we want to use degrees of freedom down here for t. We're not using n. So we're using n minus 1 times the variance of sample 1. This is n, by the way, this is n1 minus 1. And this is n2 minus 1. These are coefficients of these. This is the variance of the second sample. We add these together, but then we're going to divide back out the n, because we're just more concerned about the weighted average of the variances between these two. One might be more variable than the other. We're still assuming they're the same one, and we want to find out if that's really even very probable when we get a confidence interval. Or actually, we're wanting to find the confidence interval if they were the same, if you want to think about it, if they were the same population, for example. So we could take n1 and n2, we subtract 1, but then down here we're subtracting 2 again. So we're taking n1 plus n2, but then we're subtracting those 1s here in the denominator, so we get minus 2, so that we can use this also for our degrees of freedom. So in this case, since we're looking at two samples, we're actually going to subtract 2. So let's say we actually had, I don't know, one was 5 and one was 6, and then you add 5 and 6, that's 11, but we're subtracting the 2, that's 9. We get degrees of freedom of 9, and then our t value would be 1.8331, for example. When we do that, we can use this variance that we calculated. Notice that if one has a larger n or a larger variance or both, and when you're taking these two into account for the other sample, this one's going to win out more. We're just still dividing by the total n here for these. But if one has a higher variance or a higher n, that's going to be more represented in the actual weighted average for the variance, if you think about it. So we get this value, but we're going to use this value for both of them when we add. We're using the same variance, we're assuming they're the same variance, and we're dividing by their respective n's. When we divide by the respective n's here to get the actual standard deviation, that we multiply times the reliability factor. When we do that, if it has a lower n, there aren't as many in that sample, that gives us a little less confidence in what it is, right? So that gives us a larger value. That gives this same pooled variance basically more weight here than it does here. If n has fewer in it, or if n has a really large variance, right? When we do that, we're getting our standard deviation here, and we're taking that times our reliability factor that we found in the table using n minus 2, or n1 plus n2 minus 2, and we still got to take the differences of those averages because we're looking at the probability of we're looking at the confidence interval for the differences of the actual population averages, but we have to use the sample averages because we don't know what the actual population averages are. So we're finding confidence interval, we're doing plus or minus t times basically our standard deviation that we came up with here. When we do that, we end up with a confidence interval. So we then, on the lower end, we subtract that amount from the sample difference, and on the higher end, we add that value, the confidence interval, you do plus and you do minus. You do this equation for plus and for minus, kind of like the quadratic equation. You're looking at two different values. That gives us our confidence interval. So now, what if the actual variances are different, and we actually just want to see what the probability is of having, or what the swath is for the differences of the actual population averages, but the variances aren't even the same. We're not assuming that they're the same. Well, in this case, we got to come up with a makeshift t value here, and to do that, we're looking at the actual variance of sample 1 divided by its number. So if it's got a large number, we don't care as much about it because it's probably more reliable. And we take that times that t for that n, and then we add and we look at the variance divided by the variance of the sample divided by the the number in the second sample, and then we take that times its t value corresponding to the n minus 1 for this one. When we do that, if you think about it, if something is, maybe it has a lower n, maybe it's only like 2 values, but if they're both 6 or something like that, they're the same. It's probably, the average is probably really close to that, right? So we're not really too worried about this. Let's look at this n value here and how much this varies. Because if this is a higher, then let's just assume we're looking at this sample more than we're looking at this one. But we're still pooling, just like we pooled up here, we're still dividing though by those variances divided by their respective variances